okay, so this is what you have. So this is pretty much you had that question, 2D question of 2 legs with 1 force, right? So this is pretty much literally the 3D version of that problem. So that's how that's what we're gonna tackle today. We have another one which is fairly similar, but instead of, so this is like 3 legs and 1 force applied at the top, so it's kind of like the tripod. So you can imagine these 3 to be in compression pretty much if the force is vertical downward force. And the variation 2 is you have a plate which has some weight that's hanging from 3 cables. So if I have time, I will get to that too, but let's look at the first one first. Yes, so that's today's problem. I think from the homework though, I think one thing that you should realize from this problem, I hope that everybody got it, so I gave you 2 variations, right? So I think the original problem was taller than this one and shorter than this one. So if you compare, I mean, so similarly on this one and this one, same applied force, right? So you're applying the same force on these systems, and one, so it's pretty much same except that one's taller and one's shorter, right? So you should get compression on both legs in both of the problems. But how many of you actually did it, the homework? 5? Not too many. But did you in which case you had more magnitude of compression? In which case, so you had, I have an answer here, but however many pounds compression these bars, and these bars were also however many force compression, right? Which one did you have more force in the members? Do you remember? The shorter one, right? So the shorter these legs are, the members experience more internal force, right? Meaning that there's more force working in the member. So that means if there's more force in the member, right, that these members need to be able to endure more force, meaning that it probably sometimes needs to be fatter or stronger material or something like that. And if the whole tripod, whole system is taller, it experiences less force, so you can do away with slimmer member, right? So meaning that you can be more efficient with the material. So that's really important. That's gonna kind of come up over and over again. So depth, the effect of depth of the structure is something that you need to be very familiar with. Typically deeper the structure is, it is more efficient at resisting load, which means you can do with less amount of material. Meaning that, like, if, for example, like if you, like, the reason why trusses are like this is it has depth, therefore you can support the same amount of load with, you can already see these members are pretty slender. The reason why that's possible is it has some depth. If the truss is much shorter, those bars need to be much thicker and stronger material, which kind of defies the purpose of using the truss. So that's going to come up again and again, and that's kind of an important notion. So let's see. Let's start with this problem. So if you open the file, it actually has step-by-step explanation. So along with the video, you should have plenty of material that explains to you how to do this, but just gonna show you from scratch today. So the approach is the same, but I guess if you haven't done the 2D problem, it's a little bit a stretch, but I just want to show you how to do stuff today. But you remember how you did the 2D problem, right? Like you had this applied force, and you knew the directions of the internal forces that would be in the member, because it's going to be parallel to the member itself. So we drew these lines that we knew that was going to intersect with the applied force, and from this intersection we were able to determine like that's where this force ends, and that's where the next force starts. So what we are going to do is pretty much exactly the same process, but one more dimension. So, alright. So you have this tripod looking thing, and you have this vertical force working, pushing the point D down to the ground, right? Therefore, you must, it must be super easy to assume all of these three legs are gonna be in tension or compression. And if you want to guess and raise your voice, compression or tension, compression, right? Because it's being pushed, it's got to be in compression. So that means if I take this member DB, if it's being pushed at that end, there's got to be a force at point D along this member that's pushing back at point D, and because this member, the whole member, is in compression, I should have also, at the other end, it's gonna do that, like if I'm focusing on member DB. But I'm really interested in point D right now. So yeah, so this member is pushing back, and that's got to be the same also with all the other members. So it's safe to assume that we have all of these three members pushing back at the point somehow, right? Like that. So there should be these three forces that's pushing back at point D, and all of these, the sum of all of these three forces being equal to this, right? So it has to balance itself. So that's basically what's happening here. Let me just color. I'll give you. You guys don't need it now, but Jesus. Okay. So let me just put different colors on these three so that we know which one's which. But I just drew this right now randomly, right? So they can't be the correct magnitude. But I'm just kind of trying to show conceptually that's what's happening. But because I drew them randomly, if I add, so if these were correctly drawn, then it would be, if these were correctly drawn, if I add all of these three members, if I add this, and this, it has to close on its own, indicating that the sum of all of these four forces are 0. But because I drew them randomly right now, if I add, I can add them in 3D, right? So by connecting the end point and start point of the arrow, because I drew them at completely random scale now, it doesn't close itself. So that means basically this answer is incorrect. The direction of these are correct, but the magnitude or the scale the size that I'm showing these forces at are completely wrong. So our objective here is to figure out what the correct lengths for all of these guys are. I'm just gonna kind of eyeball it right now, just to show you. But if these, so correct answer would have a closed force polygon, so it would be something like this, even though that's not completely correct yet. But that's basically what we are trying to work towards, right? So how are we gonna do that? So we're trying to get to something where this 1, 2, and 3 will, so these 3 vectors all having, you know, these different directions connect to each other starting from point D and ending at this endpoint, which is the tail of the applied force. So we it's not there. So we basically want to have these 3 connect to each other at correct scale and end at that point. So that's basically all we're working towards. So now, let's say similarly to how we drew that diagram for 2D, please just move to the side so that we can focus on this guy. We know, let me hide that too because that's in the way. We know that, I mean, the order that we added doesn't matter either, so it's completely arbitrary, but for now let's just stick to this order. I put blue, green, and yellow in this order. So let's say this is the first one, this is the second one, this is the last one, and this guy has to end at that end point. So that's what we're trying to figure out. So now first, so we know this first force is along this direction, right? And only thing that we don't know is the where does that end. So let me just show this as a dashed line. So basically that arrow can be here or here or here. We don't know right now, but it could be anywhere along this point. But that's what we are kind of trying to locate, this endpoint of for this blue vector. So let's just say question mark for that point. So really, we don't really know where this second one should start, nor where this third one should start. Another thing that we know, though, is where this third one should end, right? That makes sense? So we're gonna locate this at the end point of that purple arrow, which is the applied force. And similarly to this, we're gonna put a line that is parallel to this force. Like this. So what we know for sure is that endpoint and that start point. And we kind of know that it's going to come from that end, but you know, sometimes if the member is in tension, it's flipped. But anyway, so we know that first arrow is on this line somewhere, second arrow is on this line somewhere, and both of those are attached to this endpoint here and here. So what we need to figure out is where this point 2 starts and ends, right? And it needs to be parallel to this guy. So this is a little bit tricky, but so if I have also a parallel line for this second arrow, I'm going to show this slightly different color so that you see it. Actually, should I put it in green? I'm going to show this as dashed line. So basically, there's gotta be a point on this line where this green arrow starts, and it's gonna intersect this first line and second line somewhere. So it's not intersecting yet, but can you see how if I move this yellow dashed line, so this needs to travel along this first dashed line, but this doesn't intersect that line, so we know this is far from the answer. But do you realize, like, as I move closer and closer and closer, now it looks like it almost intersects that line. Move closer, closer, so it's gotta be somewhere here, right? So that's basically what we were trying to figure out, is what's the correct point on this line where I can place this so that it intersects that. Is anyone lost? You following? Yeah? Alright, so the way to figure that out is, I mean, you know, you could put a million lines along this, and then if you get lucky, you intersect it. Or, I mean, and that actually suggests something. Like, if I were to put infinite amount of this line on this line, what we need to do is basically, if this line moves along that line, if the line moves in space, that's going to create a surface, right? So what I can do is create a surface by sweeping this along that line. So I'm gonna sweep, select the rail curve here, and then select the cross-section curve here, and it's gonna create this surface. And what that's gonna tell us is, if you take this intersection between this surface and that last line, right, so intersect between these two, that point is precisely where this line should end. So I can actually move this line to that point, and what that point guarantees is that it is on, because it's an intersection between this surface and this point, that point is on this surface and that line. So if I move this line to that point, right, so that's where it intersects, and basically that's the point where this blue arrow should end and this green arrow should start. So if I move this to here, right, so this blue one should end here, green should start there and end at that point, and this last one should end at that end point and start from this point. So now if I remove all of these extension line, we have three forces that are connected from head to tail, starting from point D, ending at end point. And now all we need to do is, right, so these were all at wrong scale, but if I now move this to the original point, to point D, end point being right there, and that's how big each of the forces are in each of these members. And then we are going to determine, in this case, the scale that we are using is 50 inches equal 50 pound, so 1 inch equals 1 pound. So if I get the length of this arrow, that's 18.05, so I'm just gonna say, for the sake of simplicity, I'm just gonna say 18. That, if you get the length, it's also 18, so 18 pound, 18 pound force here. That, if I get the length of that, that's 20.03, so that's 20 pound force. Does that make sense? Yes.
Can you demonstrate how to do that parallel again?
Of course. So I kind of ran through it quickly because I wanted to kind of show the process smoothly. But you kind of conceptually got the process, right? So I would kind of do it more carefully. So All right, so this is that 50-pound force is what we are trying to equilibrate, right? And we know the, I think, yeah, we know the direction of all of these three forces, which is basically these three legs, right? So let me show this line type dashed, and actually let's color this according to the force. So we have the blue, green, and yellow. I'll show them as dashed line. So line 1, line 2, and line 3. So, and we have a start point, which is end point of that arrow. It should start here and end here. So that's what we are trying to work towards. And this is, let's call that number 1. I mean, you don't have to put all of these dots. I'm just trying to do it for explanation purposes. But we have number 1, number 2, number 3, right? So we want to put number 1 starting from the start point, number 2 starting from somewhere on number 1, and then number 3 ending at end point. So what I'm going to do is put the number 1 on here, the start point, right? I'm gonna make it really big so that it's kind of infinite. That's probably too long. So about this long. So that's one line. Is it hard to see? Should I do a black? Right, it's better. I'm gonna put this number 3 at the end point. So yellow line basically ending somewhere at end point. Well, ending at end point, but starting somewhere. So that's simple, right? So that first line intersects the start point. The third line intersects the end point. The tricky part is you have to have a second line somewhere on here, and you want to be big enough so that it covers the whole thing. So you want to create a surface by sweeping this line, green line, along this blue line. So what you do is you can type in sweep 1, or you can go to surface sweep 1 rail, and it's going to ask you to select the rail, which is the path of that sweep, which is in this case blue, right? And then select cross-section curves. That's the one that you're flying through the space. So you select the green, and that's gonna create that surface, right? Then what you do is you want basically a intersection point between this line and this surface that we just created. So we type in intersect and select objects intersect. So first thing I select is this line, and next one is the surface, and enter. You get that intersection point. And so that's basically where this green line, which is at the edge of this surface, should be. So I'm gonna copy this green line to that point. Now you're guaranteed that green line intersects with the yellow as well as the blue, right? So now you can kind of delete this surface. So now we have 3 infinitely long lines that's intersecting with each other. So I can basically, so now we know that the first arrow, let me lock this, but first arrow should go from this start point and end at the intersection of these first 2 lines. So So that's the first force. Second force should start from there and end at next intersection point. And the last one should start from this intersection point and end at that end point. And those three are the forces at correct magnitude at that point. So let me see. So if I copy this to the point D, that's basically the answer for that point D. Did someone have a question? Yeah.
At first you said that the number should add up to the force that's pushing down.
Mm-hmm.
But whenever I add it up, it equals to naught.
Right. So actually, that's a really good question, and that's really important to know. The difference between vector addition and arithmetic addition, right? So because we're talking about vector calculation, and I think I had a slide in the first class, but adding the vector doesn't mean so if you add the lengths of vectors just like the pure math, you're gonna end up with, so yeah, that's a different thing than adding the vectors. So it's, if you end up, so yeah, so right now if you add 18, 18, 20, that's 56, so that's not equal to 50, and that's correct for vector because you're taking into account all these different directions. If you're, the only time that's correct is if all three vectors are in the same direction as the original applied force. So if we have, like, let's say if you had a piece of board with three legs, completely vertical, and then if you had a 50-pound force, right? And let's say this was, so I mean that's like three-legged stool or something, right? And if I sit down, that's like 150, and it's probably gonna be like equal distribution, so you should have like 50, 50, 50. So, but that's only because the direction of all of these three members are parallel to this original vector. So that's the only time your mathematical addition of the magnitude should be equal to the original. So if any of these legs have a different direction, then your addition, your number addition should be slightly different. So that makes sense. So because this is a little bit tricky to do, I wanted you to, so why don't we do this? So we were able, well, it's gonna be the same answer, doesn't it? So why don't we do, take the original problem here, maybe scale this original force by like 1.5. Well, actually no. What we should do is, why don't you, okay, why don't you grab, okay, so let's copy this for your practice, right? So let's copy this original question to the side. Why don't you grab this original applied force, turn the edit points on, right? You can click on that button, or you can type in points on, and grab the tail of this arrow and move it slightly. So now all of a sudden you have this weird diagonal force acting on this member, right? So what I want you to do is to follow the same exact procedure and figure out three forces that that equilibrate this force. So the total addition of the vectors end up being 0, so meaning that that force polygon should close. So you should, and then figure out the answer. So the answer is going to be different for everybody, but the process is exactly the same. So how much time do you have? 20 minutes. So I want you to kind of practice and make sure that you understand the process. So you think you can do that? So I'll walk around, and then maybe I'll give you 10 minutes, and then maybe I'll follow that same process again.